Okay, so I'm going to try to zoom in on this, but I'm not sure that you've seen all of these fractals before.
I think I've seen all of them. Just seeing them made me remember them.
Okay, great. Yeah, well, I think I've got most of them. Let's start with the Sierpinski Triangle.
Okay.
Okay, so I scale it by a factor of 2. So what happens now?
Well, in the diagram, it looks like you just get a bigger, sort of a bigger Sipinski Triangle.
Mm-hmm.
But
I started with this one, and then I scaled it by a factor of 2, and I got this.
So I guess the Sipinski Triangle is made by just going it's already going infinitely small.
Uh-huh.
Scaling it up creates 3 copies.
Okay.
Here, here, here.
So now this time I got an interesting situation where I scaled by a factor of 2, and now I got 3 copies.
Yeah.
Okay. So now by our formula, 3 equals 2 to the dimension.
Yep, so this would be a non-integer dimension.
Yeah, do you know how to solve this equation? I don't remember how much we've talked about how to solve these kind of equations.
I don't think we've talked about it much.
Okay. So these equations are solved by something called logarithms.
Yes. So I think it would be log 2 of 3 equals d.
Log base 2, 3 equals d. That's right. Or we can say it's log of 3 over log of 2. Either way is actually fine, as long as I zoom out enough. But yeah, so the dimension, using Dave's definition, the dimension of the Sierpinski triangle is log base 2 of 3. So let's look at the Koch curve next. Do you remember what the Koch curve is?
So either you sometimes you can create it with the Koch snowflake, which is an equilateral triangle, but in this case it's just a line, and you take the middle third and you sort of turn it into an equilateral triangle on the surface. So like for the first...
Alright, here, yeah, why don't you draw out the first couple?
So you'd start with something like this, and then you would take the middle third and sort of pop it up like this.
Mm-hmm.
And then you would do that again for the middle thirds of all of the other segments that are formed.
Okay.
So just look like this, and then you would keep doing that forever.
Okay, great. So this, in his example this time, he scales it by a factor of 3.
Okay, so you scale it up by 3.
And then I'm going to cover up how many copies, even though you might have seen it. So how many copies of the original Koch curve do I get when I scale this by a factor of 3? What happens? What have I found?
So it turns into this, but then you also see this shape here, 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 and here.
Uh-huh.
So you get 4 copies.
Okay. So we get 4 copies.
4 equals
3 to the d.
So this would be log base 3 of 4
Right.
would be your dimension.
Which he says is about 1.26. Okay. But let's just say that that's 1.26 dimensions. So I guess that this is the one that shows up the best. So what do you think that means? That this is 1.26 dimensional?
Well, I don't know. I would have said before that this Koch curve shape lives in 2 dimensions because you can get to all of the points on the curve by going in these in the horizontal direction and the vertical direction.
Okay.
But 1.26 means it's higher than 1 dimensions, but not quite 2 dimensions. So it would be less than a two-dimensional shape, which is interesting.
Yeah, that is interesting. Okay, so for the last video, let's talk about the one he hasn't drawn a picture of and see if we can figure it out.